Okay, so let's do an example of diagonalization and its applications. So let's consider matrix A. On the first row, 7, 2. On the second row, -4 and 1. First of all, let's diagonalize the matrix A. That means find the diagonal form on a diagonalizing matrix. And then after we do this, let's see what interesting things we can do with that. So first step, let's find the characteristic polynomial, which is determinant of A minus lambda times identity matrix equal to 0. A shortcut for 2 by 2 matrices is the following. Lambda squared minus the trace of A times lambda plus the determinant of A equals to 0. There's the characteristic equation, where the trace is sum of diagonal elements, so 7 plus 1 here, and the determinant is 7 plus 8 is 15. So the characteristic equation will be lambda squared minus 8 lambda plus 15 equals to 0. Or we can do it the usual way, so subtract lambda from diagonal elements and calculate the determinant. Okay, so we got the characteristic equation. Let's solve to find eigenvalues. So lambda minus 3 times lambda minus 5 in this case easy to solve, equals to 0. So we'll get lambda 1 equals to 3 and lambda 2 equals to 5, the two eigenvalues of the matrix A. Now, for each of those eigenvalues, in the next step, we have to find an eigenvector. So let's try to take them one after the other. So lambda 1 equals to 3. To find an eigenvector, we have to find a non-zero vector v, such as a v vector equals to 3v vector, or v non-zero. So, in other words, 7 to minus 4 and 1 times pq, which is, let's call this, let's say this is v, equals to 4p 4q. Or we can rewrite it as A minus 3 identity matrix times V vector equals to 0. So let's try to simply basically subtract 3 from diagonal elements of A. So the matrix A minus 3I will be 7 minus 3 is 4, 2 minus 4. Subtract 3 from 1 is minus, subtract 3 is minus 2. Multiply by PQ, the vector V, equals to 0, 0. As a sign that we can write more, the two equations we get after writing detailing the matrix product here will be proportional. So 4p plus 2q equals to 0, and the second equation will be redundant. So minus 4p minus 2q equals to 0, which is we not is redundant. So basically, we just solve for this one and get q equals to minus 2p. So to choose an eigenvector for the eigenvalue 3, we have to choose, is the same thing as choosing a vector, any vector, non-zero vector pq with q equals to minus 2p. So let's do the choose the simplest possible way. v1, the eigenvector for the eigenvalue lambda 1, will be, let's say p is 1 and q is minus 2. Q is minus 2p. So we got an eigenvector v1 corresponding to the eigenvalue lambda 1 equals to 3. So let's try to erase all the work and then write down only the result. So the vector for the eigenvalue lambda 1 equals to 3, we will get eigenvector v1 equals to 1 minus 2. Okay, let's do the same for the other eigenvalue lambda 2 equals to, let's say it's 5. Okay, so basically let's do it faster. So subtract 5 from the diagonal elements and say 7 minus 5 is 2, 2 minus 4 and minus 4 multiplied by the vector b, which is pq, equals to the null vector 0, 0. So basically, again, the two equations 2p plus 2q equals to 0, and the second one is redundant, minus 4p minus 4q equals to 0, so we only need to write this one, p plus q equals to 0. So q equals to minus p. Okay, so we can say pick up based on this criterion. Let's select the eigenvector b2 to be q equals to minus p. So select p equals 1 and q equals to minus. Okay, so we are done with this. So now we got two eigenvectors, right? So b2 equals to 1 minus 1. In any case, for any n-bar matrix with distinct eigenvalues, in any case, we know from in advance that it's diagonalizable. So how to so now we know that the matrix is diagonalized, but how to find the diagonalizing matrix? The diagonalized matrix T, it's very simple recipe. Just put the vectors v1 and v2, the eigenvalues we got for the eigenvalues lambda 1 and lambda 2 respectively, put them as column of a diagonalizing matrix. So v1 here and v2 here. So that's the construction of the diagonalizing matrix. In this case, in this special case, is 1 minus 2, which is that will be v1, and 1 minus 1, that will be v2. So what's so special about this diagonalizing matrix? Simply this equation T inverse A T is diagonal. So that's the diagonal form. And in this case, since the eigenvalues are 3 and 5, the diagonal form will be 3, 0, 0, 5. Not the important thing. So the order of the listing of eigenvectors when we build the diagonalizing matrix T is first v1 corresponds to eigenvalue 3, second v2 corresponds to eigenvalue 5. This matches exactly the order of the listing of eigenvalues in the diagonal form. First eigenvalue 3, second upper left eigenvalue 3, lower right eigenvalue 5. So the order of eigenvalues in the diagonal of the diagonal form matches the order of the listing of the eigenvectors in the matrix T. So if we put just hypothetically v2 first and v1 second, then T inverse AT will be 5, 0, 0, 3. So we'll be careful with the order of the listing of eigenvectors in the diagonalizing matrix T. Is the same with order of the listing of the eigenvalues in the diagonal form. Okay, so we have T inverse AT equals to D. Just in case, so let's try to, because I need to erase a couple of mistakes here to continue. So we got a diagonal form equals to 3005. Diagonalizing matrix T is 1, 1 minus 2 minus 1. And on the spot, we'll need it later. T inverse. What's the formula for the inverse of a 2 by 2 matrix? It's easy formula. 1 over the determinant. What's the determinant of this? 1 times minus 1 is minus 1, minus minus 2 is 1. So determinant is 1, so 1 over the determinant is 1. So we don't write anything here. The main diagonal elements will be flipped, so minus 1 and 1. And secondary diagonal elements will acquire a minus sign. So minus 1 here and 2 here. So that's T inverse. Okay, so now let's try to keep this one. this relation is very important relation. P inverse A T equals to D. Right. But if we want to calculate function matrices, even more important than this one is an equivalent relation which expresses A in terms of D. This is a non-commutative equation, how to clean up from around A. So let's multiply the left-hand side and right-hand side to the left by T and to the right by T inverse. So the left-hand side will multiply to the left by T and to the right by T inverse. The right-hand side again the same, to the left on the left by T and on the right by T inverse. So if we do this to the left-hand side, T and T inverse will simplify, T and T inverse, they simplify in the sense they get identity matrix. We get a clean A here. A will be T, D, T inverse. It's a very important relation. So let's try to, let's keep this relation A equals to T, D, T inverse and see which are the multitude of consequences of this relation, A equals to T, D, T inverse. At this moment, let's see, we want to calculate any function of the matrix A. So this is a very general principle, a function of the matrix A. Like A to the power n, right? N power, stuff like this, exponential of A or exponential of AT. F of A will be T, and then multiply, apply this function to the eigenvalues. So F of lambda 1 and F of lambda 2 here, and then 0, 0. Because applying this function f to the diagonal metric amounts is very simple. It amounts to applying the function to every diagonal entry times T inverse here. So this is a very general principle. For example, well, sinus of A, for example, will be T times the matrix sinus of lambda 1, 0, 0, sinus of lambda 2, T inverse. Okay, so now let's try to apply this theory to calculate some two things. Let's do first the calculating the nth power of the matrix A, and second, we'll explain how to use this theory to solve system linear differential equations. Okay, so let's see. Let's keep whatever is really useful here. So not only A equals to T, D, T inverse, but more generally, any function of A equals to T times F of 3, 0, 0, F of 5, T inverse. Any function of A can be expressed as diagonalizing matrix T times the diagonal matrix which has on the main diagonal the results of applying the function f to the eigenvalues times the inverse of the diagonalizing matrix T. Okay, so example 1, so application 1. Let's use these principles we discussed about to calculate A to the power n. A to the power n will be diagonalizing matrix T, which is 1, 1, minus 2, minus 1. Then apply the function nth power to the eigenvalues, so 3 to the power n, 0, 0, 5 to the power n, times the inverse of the diagonalizing matrix, minus 1, minus 1, 2, 1. We have to be very careful that the matrix product is not commutative, so we are not allowed to switch at will. So first of all, let's calculate the product of these two. Let's see what we get here. First row, first column, I will get minus 3 to the power n. First, second, again minus 3 to the power n. Second, dot product with first, 2 times 5 to the power n. Second, Dot product in the second row here, second column. We get 5 to the power n. So that's the product in the second matrix and the third matrix. Now, with the first matrix on the left, multiply the last obtained matrix. So this multiplied by this. Let's see what we get here. First will be 2 times 5 to the power n. 2 times 5 to the power n minus 3 to the power n. First, second, dot product. So 5 to the power n minus 3 to the power n. Second, first. 2 times 5 to the power n minus 2 times 3 to the, so let's see, 2 times 3 to the power n minus 2 times 5 to the power n. 2 times 3 to the power n minus 2 times 5 to the power n. So I want second first here. Second first. 2 times 3 to the power n minus 2 times 5 to the power n. And finally, second. 2 times 3 to the power n minus 5 to the power n. And this matrix is the explicit form for the n powers of a to the power n. So basically, so let's write in a single row the matrix 7 to minus 4 and 1 to the power n equals to this one. Let's get a routine check. So what does the zeroth power? Any matrix the power 0 is like behaves pretty much like every number. The power 0 is 1, but what is 1 for numbers is identity matrix for matrices. So let's see, if we set n equals to 0 here, do we get identity matrix? Of course we do. So all the exponentials are to the power 0 are 1. So we'll get a 1 here, 0 here, 0 here, and 1 here. What about if we set n equals to 1? Do we get any matrix the power 1 is itself. So you set n equals to 1, get 10 minus 3, 7, 5 minus 3, 2, here 6 minus 10, 2 times 3, 6 minus 10 is minus 4, and here 6 minus 5 is 1. So sometimes it's good to do these routine checks to make sure you didn't do any obvious mistake. So that's the first possible application of that. The second application involves solving linear systems and differential equations. Okay, so let's still remain based on this matrix just to show the idea how it works. Application 2. How to use this diagonalization to solve related system linear differential equations. So the unknowns are x1, x2, the two unknowns functions, and the system is like this: x1 prime equals to 7x1 plus 2x2, and then x2 prime equals to minus 4x1 plus x2. In other words, in a concentrated form, if the vector x is the vector of the unknown functions x1 and x2, x1 and x2 are the unknown functions. Prime refers to, let's see, both x1 and x2 are functions of t. x1 equals to x1 of t, and x2 equals to x2 of t. And these are the two functions that must be we must find, right? So let's rewrite this system of equations in a vector form. So x prime, how differentiate the vector? Differentiate every component of a vector equals to the matrix A times x. Okay, let me throw in some initial conditions. Let's say x1 of 0 equals to 11, and x2 of 0 equals to minus 7. These are the initial conditions. And together, all of them will be an initial value problem. So we get x prime equals to ax. This is the system of these two equations is equivalent with this one in a vector form. And x of 0 equals to 11 minus 7. And this will be the initial value problem. X prime equals to ax, and x of 0 equals to the vector 11 and minus 7. What is this? This is like we discussed about separable equations. For example, if we got, let me go back to the period we discussed about separable equations. Let's remember if we have dy over dx equals to ay, right? How do you do? So basically, we record dy over y equals to a dx. We integrate both sides, right? And get logarithm of y equals to ax plus log c, and then exponentiate both sides. We get y equals to c e to the power ax. There's the general solution of this equation. So let's inspire ourselves from this previous work on separable equation and write down the solution of the vector form equation. X prime equals to ax. So this one means x of t, of course, equals to the exponential of a times t multiplied by the vector of initial conditions, which will be 11 and minus 7, which will be x of 0. This is a very general principle. To solve a series of linear differential equations in vector form, x prime is a n by 1 vector, is an n by n matrix times x again n by 1. Is the solution is the exponential of at times the vector of initial conditions. Okay, so let's try to do first the exponential of at. So we need some space here. So the exponential of at is again t times e to the power 3t 0 0 e to the power 5t. So the exponential of element times t is applied to every diagonal element. So exponential of 3t, exponential of 5t on the diagonal times t inverse. And this will be t 1 1 minus 2 minus 1. This is diagonalizing matrix t. Exponential of dt is, so this exponential of dt, e to the power 3t 0 0 e to the power 5t times t inverse. We got it from there, minus 1 2 1. Okay, so let's see what it is. Let's do the product of these two. First, we get minus e to the power 3t. First, second, minus e to the power 3t. Second, first, 2 times e to the power 5t. Second, e to the power 5t. Now we have to multiply these two. Let's enter the result here. First, first, 2 e to the power 5t minus e to the power 3t. First, second, e to the power 5t minus e to the power 3t. Second row, first column. So 2 e to the power 3t minus 2 e to the power 5t. And finally, second. 2 e to the power 3t minus e to the power 5t. And this being exponential of a times. Okay, now we need one more step to perform in order to find the solution of the system of linear differential equations. So we need to multiply the exponential of at by the vector of initial conditions 11 times 7. Okay, so let me erase the work before. So x will be exponential of at times x of 0, which will be what? That exponential, we can put 2 e to the power 5t minus e to the power 3t, e to the power 5t minus e to the power 3t, 2 e to the power 3t minus 2 e to the power 5t, and 2 e to the power 3t minus e to the power 5t, multiplied by the vector of initial conditions, 11 minus 7. Okay, so we get to what we have here. So this is, okay, first, let me put here like a bottleneck just to make sure that we know we see exactly the right places for everything. So we get 22 e to the power 5t minus 11 e to the power 3t minus 7 e to the power 5t plus 7 e to the power 3t. Lower row, so we get 22 e to the power 3t, 22 e to the power 3t minus 22 e to the power 5t minus 14 e to the power 3t plus 7 e to the power 5t. And this will be x1, the top element will be x1, and the bottom element will be x2. So let's try to write them down. So x1, let me write them down here. x1 of t equals to, let's group the like terms here, is 22 minus 7 is 15 e to the power 5t. Minus 4 e to the power 3t. X2 of t equals to, let's count e to the power 5t first. Minus 22 e to the power 5t plus 7 e to the power 5t is minus 15 e to the power 5t. And let's count the e to the power 3t's first. 22 e to the power 3t minus 14 is plus 8 e to the power 3t. And this will be the solution of the system of linear differential equations written here. x1 prime equals to 7x1 plus 2x2, x2 prime equals to minus 4x1 plus x2, x1 of 0 is 11, x2 of 0 equals to minus 7. Just in case, just check, set t equals to 0, and we need to recover the initial conditions. So we get 15 minus 4 is 11 for x1, and minus 15 plus 8, because exponential of 1, is minus 7 for x2. So that's another important application of diagonalization, solving in some cases system of linear differential equations.